All right, so in the last video, we derived the energy balance for a shell and tube reactor. So basically, we looked at deriving the balance for the tube part. And then at the end, we said we can think of at least 3 different ways where that we would have a coolant in this shell part and how we would derive the balance for that. So one of the ways was we have a coolant coming through in this shell part, and maybe the coolant is the flow rate is very high. So because the flow rate's really high, the fluid is exchanging heat with the contents of the reactor, but the temperature of the coolant isn't changing that much. In that case, the energy balance that we derived for the reactor is set because we have a term in there, a TA term, that accounts for the temperature of the cooling fluid. However, that's not always the case that temperature will remain constant. So in this lecture, we'll look at 2 different scenarios. One where we have a co-current heat exchangers, so we have cooling fluid entering at the same point as the reactants, and the temperature of that cooling fluid is changing along the length of the reactor. We'll also look at countercurrent. So in that case, we have cooling fluid coming in the shell part at the place where the products are discharging the reactor. And so in that case, also the temperature of the cooling fluid is changing as it travels down the reactor, but we have to treat our solution a little bit differently since it's entering at a different point than the reactants. So that's what we're going to do here. So if we scroll down to our notes, what if TA is not constant? I need to write a balance on the heat exchanger fluid. So I have 2 scenarios here. I have co-current coolant flow, and I have countercurrent. So let's look at the co-current scenario first. So if we want to derive the balance for the cooling fluid, so we'll say derive So this is what we're going to use to account for the fact that the temperature of the cooling fluid is not constant over the volume of the PFR. So if we go back to our system here, the cooling fluid, we're going to derive a balance as a function of V down the reactor. And we already know what that balance is going to look like. So the cooling fluid is going to be exchanging heat with the contents of the reactor pursuant to a overall heat transfer coefficient times an area times a temperature difference. So we can go ahead and just write that down, similar to how we wrote the balance for the reactor contents. And you'll see that this is going to look a lot the same. So we have our A term. This is the same U term as in the last case, and our A term is the same A term as in the last case. So if you're writing a balance, actually I should put an A here. If you're writing a balance on the reactor fluid, the overall heat transfer coefficient and area that you use are the same that you will use when you write the balance on the temperature of the reactor. Notice that I added this A here. We are denoting the temperature of the cooling fluid, TA. The lowercase a stands for ambient. That's why that symbol is used. So now we know that the temperature is going to change pursuant to a UA delta T, a temperature difference. And in the last case, we said that what we want our temperature term to do, so we're going to write in here a delta T, and we want to ensure that the way we order the temperatures is going to allow heat to transfer in the physically correct way. So when we were writing a balance on T, which is for the reactor fluid, inside the parentheses we had TA minus T. And what that meant was when the ambient temperature, or the temperature of the cooling fluid, was higher than that of the reactor fluid, then the temperature would increase. So this term would be positive, and hence T would increase. On the other hand, if T was less, or with T was greater than TA, in that case, this term would be negative, and in that case, T would decrease. So we have to make the same argument for, now that we're looking at TA. If TA is greater than T, that means that the cooling fluid will transfer heat to the reactor contents, and hence the temperature of the cooling fluid, TA, will decrease. Whereas if TA is less than T, then the reactor contents will transfer heat to the cooling fluid, and hence the temperature of the cooling fluid will increase. So because of that, we write this the opposite way as we did before. We're going to say T minus TA. And again, this is done to ensure that the derivative of TA with respect to volume either increases or decreases based on the instantaneous temperature difference at that point in the reactor. So just like in the prior case, we're going to divide this by a sensible heat term. So one of the nice things about this reactor, or this cooling fluid, is that it's going to have a significant heat capacity, so it's going to be able to absorb a lot of heat. We're going to write this as an MC, C for cooling fluid, CPC. I've written this as a mass flow rate. This could be a molar flow rate. The important part is that if the heat capacity is written in a per mass basis, this is a mass flow rate, whereas if the heat capacity is written in a per mole basis, this is a molar flow rate. So again, just making sure that units work. So we'll say here, coolant flow rate, and here is the coolant heat capacity. So again, a larger value of heat capacity for the coolant is going to mean a less dramatic temperature change, which is going to be, if for a cooling scenario, is going to be a more effective coolant. So that's our balance. If we have co-current heat exchange, this is our fourth balance. We include this with our other design equations, and we can solve our reactor design. So in our countercurrent case, the physics are essentially the same. So if we go back here and look at our system, now we have reactants flow or reactor flow going this way, and we have coolant flow going this way. The balance on the temperature of the cooling fluid is essentially the same as in the co-current case, except that the limits of integration are switched. So my inlet condition, so where I start my integral, is here, whereas in the co-current case it was here, and where I end my integral is now here, whereas in my co-current case it was here. So I really just have to write the same balance, but now I'm going to switch the limits of integration. So when I switch the limits of integration, one way that I can do that is just to simply write the differential equation as the negative value of what it originally was. So if I go down to my countercurrent case, my differential equation is going to look like this. Negative UA T minus TA. And this basically just says I'm putting this negative sign here because instead of integrating from the inlet point to the outlet point, I'm integrating from the outlet point to the inlet point when I'm talking about V. So we have set up V such that V equals to 0 as at the inlet of the reactor fluids. But for the cooling fluid in the countercurrent case, that's the reactor exit. So when I have my system of ODEs in the case of a non-isothermal PFR with a countercurrent heat exchanger, the balance on the cooling fluid has opposite limits of integration as the other ODEs. Rather than integrating it separately, which would then mean that I would lose an equation and not be able to solve it, I instead integrate it along with the other ODEs, but switch the limits of integration. And the way I do that mathematically is just to put a negative sign out front. Sometimes you will see that instead of putting a negative sign out front, these two values will be switched. So you will have no negative sign, and instead you'll have TA minus T in parentheses. Either way is fine. So finishing up here, I have an MC CPC, where the C indicates heat capacity, and again, I can have in the denominator here a mass flow rate or a molar flow rate as long as my units are consistent. So there's one more thing I need to account for in this countercurrent case, And that's that I know the temperature coming in here. This value is specified. I know what temperature the cooling fluid enters the reactor or the shell. I don't know the temperature here. And to be honest, when I'm doing these energy balances, I usually know the inlet temperature, not the outlet temperature. But again, since the way I've written this problem, the countercurrent flow, the inlet temperature is at the exit point. So the way I've defined volume, volume starts here and proceeds this way, but this is V equals to 0. So I don't know the temperature of the cooling fluid at V equals to 0. I instead know the temperature at V equals to V. So because of that, when I do my solution, when I'm giving an initial condition, what I'm essentially saying is, what is this temperature? So I have to, and I don't know that. I would have to solve the balance to know that. So what I do is I specify this value, and then I see, does that result in a temperature here that is the inlet temperature that's specified? So this becomes a guess and check solution. I guess an initial condition, which means I'm guessing a temperature at V equals 0, and then I see if the final temperature, which for the countercurrent heat exchanger is actually the inlet temperature, if that equals the specified temperature. So that's a lot to take in. We'll do an example next that hopefully illustrates it. But anyways, I need to account for one thing. I don't know TA at V equals 0. I know TA at V equals V. So I don't have an initial condition. Therefore, I need to guess one. Until I arrive at a value of TA at V equals V that equals the specified inlet temperature. And we'll practice with this next.